Okay, welcome back. This is the video lecture for Chapter 3, Section 2, Unit Vectors and Adding Vectors by Components. Okay, so we learned in the previous lecture how to add and subtract vectors using a graphical method, the head-to-tail method it was called. And that's fine for drawing sketches and simple pictures to give us a feeling for what a resultant vector is when we add or subtract multiple vectors. But it's not really going to be enough for quantitative calculations where we need numbers. When we need accuracy with numbers, we're going to need an analytical method for adding and subtracting vectors, a method using algebra. And that's what I'm going to talk about in this lecture. Okay, so on the slide before you, the first key idea in this lecture is to introduce the concept of a unit vector and vector components. I spent a good bit of time in the previous lecture talking about how you calculate what are called the scalar components given two things, the magnitude and the direction of a vector. Right? Again, given the magnitude and direction of a vector, we need to be able to calculate the scalar components of that vector. And that's what we talked about in the previous lecture. Okay. We're going to introduce now unit vectors and what are called vector components. Let me try to put your mind at rest here at the beginning of this video and say that the concept of a unit vector, which we're going to talk about here first, is not meant to be subtle or tricky or deep. So don't overthink it. I think a lot of students, when they're first learning about unit vectors, feel like there must be something more to it than what they're thinking, and therefore that they get all confused. It's really not meant to be terribly complicated. Let me explain. First, let's just be clear about the definition of a unit vector. First of all, it's clearly a kind of vector, but it's special vector. The key things about it are a unit vector is what's said to be a dimensionless quantity. Dimensionless boils down to no units. Okay? So there are no units associated with this special kind of vector called a unit vector. Here's the next key thing, and this is where the name comes from. The magnitude of a unit vector is equal to 1, exactly 1. By definition, its magnitude is 1. And as you may know, unity is in mathematics a word for 1. Unit vector, the name unit in there is implying something about 1. The 1 comes in that the magnitude of a unit vector equals 1. So what is it that a unit vector does? Well, like any vector, it points, but a unit vector's purpose is to point in a specified, chosen direction. Let me introduce two of the three unit vectors you might come across. Look carefully at the slide. I'll draw it over here to the side in case you can't see it here. But the first unit vector is called I hat. If I draw the symbol larger over here to the side, the lowercase I, without a dot on top, instead a caret, called a hat. Okay? That's the unit vector symbol, I hat. What is its job? I've drawn it in the picture down here in the XY coordinate system. It has one job only, to point in the plus x direction of your coordinate system. It's like a little signpost that points in the plus x direction. Next unit vector is pronounced, its name is pronounced J hat. I'll write it over here. J, but without it, don't put a dot on top, put a caret called a hat. J hat. And it is a unit vector that points in the positive y direction. Here it is. Okay? That's y hat. Excuse me, J hat. I beg your pardon, J hat. Okay, they're like little signposts. I hat always points in the plus x direction. J hat always points in the plus y direction. Now here's something to think about. A lot of times objects move around not in two-dimensional space, but in three-dimensional space. In that case, don't we need a third coordinate axis? We need x, we need y, and we need a third one. What's it called? And is there a unit vector for it? Maybe some of you know. Do you know? Well, the third coordinate axis is called z. And if you draw a picture like you see here on this slide, with x and y in what we call the plane of the screen, but perpendicular to each other, right, at a right angle, the third coordinate axis, z, must be perpendicular to both x and y, so the only option is for it to be perpendicular to the screen. And given plus x to the right and plus y up in the plane of the screen, plus z would be pointing directly out of the screen. And sometimes we have to deal with three dimensions. We'll be seeing that later on in the course. But you might as well get used to, or at least see for the first time, a way we'll often try to draw a full three-dimensional coordinate system. Of course, we're limited to drawing it on a two-dimensional surface, so we have to try to represent three-dimensional axis coordinate system on two-dimensional surface. So there's plus x, and there's plus y, and then you kind of draw the third one and label it z, going like so. So that's all supposed to be right angles there. And that's really supposed to imply to the reader, x is to the right, y is up in the plane of the screen, and z is coming straight out towards you. Okay? And then, given that kind of a drawing, the unit vector pointing in the z direction has a name and a symbol. It's called k hat. Okay? So the answer to this question, yes, there is a unit vector pointing in the plus z direction, and it's denoted k hat. Okay, so we have just introduced three somewhat unique, special vectors called unit vectors. They have no dimensions. They have magnitude equal to 1, and they just point in their assigned directions. I hat points in plus x, j hat points in plus y, k hat points in plus z. So that's technically all we're going to say at this point about unit vectors. Now we're going to start to use them, and we're going to introduce the concept of vector components. Okay, so here comes our next definition. What is a vector component? We learned how to calculate scalar components in the previous lecture. The vector components of a vector are what you get when you take its scalar components and multiply them by the corresponding unit vector. So if you know the scalar components, let's take a two-dimensional situation. So you know the x scalar component and the y scalar component of a vector. Multiply the x scalar component by the corresponding unit vector for the x direction, I hat, and you'll have the x vector component. Take the y scalar component and multiply that by the corresponding unit vector for the y direction, that's j hat, and you have the y vector component. So that's what I'm showing you in this kind of word equation right down here. So here we have a vector A, or if you like, you can see it over here. I've drawn it. It's got its tail at the origin. It's pointing out into the second quadrant of the coordinate system. And if we had a drawing like that, we know from the last lecture how to draw the scalar components. The scalar components are the projection of that vector onto each of the coordinate axes. So we have AX pointing to the left and AY pointing up with regular arrow tips, okay? Like that. Those would be the scalar components, AX and AY. And we would, in principle, be able to calculate the numbers for ax and ay, okay, if we know the magnitude and the direction of a. So if we know ax and ay, then we multiply ax by I hat and ay by j hat, and we get full-blown vectors. Ax times I hat, right here, is called the x vector component of A. Ay times j hat is called the y vector component of A. And now those components are full-blown vectors, hence their name, vector components. And so now look carefully at this vector drawing that I have over here with the vector A pointing into the second quadrant. Look carefully at this arrow down here, which I've labeled ax times I hat, meaning it's the x vector component of A. Notice the drawing shows the arrow with an open tip, like that. Remember, that's your book's way of denoting a vector. Okay, so ax times I hat is a vector in its own right. It's called the x vector component of A. Now look at this arrow right here. It also is drawn with an open tipped arrow. I'll draw it over here to the side. You can see it clearly like that, meaning it's a full-blown vector in its own right. It's called the y vector component of A. Okay? All right, so notice something else now. Ax and ay, I should say this, ax I hat and ay j hat, the two vector components, are drawn, look at what I've just circled, head to tail, one after the other. And then A is drawn from the tail of the first to the head of the second. That's the rule for vector addition. In other words, the vector A is equal to the vector ax I hat plus the vector ay j hat. And that's what I have right here. Okay? Okay, so we just take the scalar components of a vector and we multiply each by its corresponding unit vector, and we get vector components. And you add the vector components to get the full-blown vector. And this expression that I've highlighted with the yellow highlighter, writing A in terms of its vector components added together, is said to be a vector in unit vector notation. It is very handy. And if you are given in a homework problem a vector expressed in unit vector notation, you should be thrilled. Why? Let me give you an example. Suppose you're given in a homework problem that there's a vector capital A given by -2 meters times I hat plus 3 meters times j hat. That's a vector that's given to you in what we call unit vector notation because of the I hat and the j hat. Comparing that expression to the highlighted expression on the left, we can immediately write down what the scalar components of the vector A are, which we would just denote ax and ay. The x scalar component is whatever multiplies the I hat, in this case, -2 meters. And the y scalar component is whatever multiplies the j hat, in this case, +3 meters. So we see, if we're given this vector A in unit vector notation, that it has a negative x scalar component and a positive y scalar component, just like might be the case with the vector A that you see in this drawing. Okay, we're going to be practicing with using unit vectors in the class sessions, so you'll get a chance to build up some familiarity with that. But I have one more key idea in this video. Very important. It is the analytical method for adding and subtracting vectors that I talked about at the beginning of this lecture. The procedure for vector addition and subtraction by components. We use the components. And the idea is really very simple, but we have to be able to do it. Okay? Okay, here's the idea. Suppose somebody has come along with three vectors. They're labeled little a, little b, and little c, each with an arrow on top because it's a vector. And we are tasked with adding those three vectors to get the net, or total, or sum, or resultant, whatever word you want. That's what this line right here means. I called the resultant R. R is what you get when you add A and B and C, but vector addition. Now we could try that vector addition using the head-to-tail graphical method, but that's not going to be really quantitative for us. Here's the way we're going to do it. I'm assuming that we are given enough information that we know the x and y components of A, B, and C, the scalar components. If you know the scalar components, it's easy to get the vector components. Multiply each scalar component by its corresponding unit vector. Let's say we know the scalar components of A, B, and C. Then all I want to do is find the scalar components of R, the sum. Okay? And it's very simple. To find the x scalar component of R, take the x scalar component of A, add it to the x scalar component of B, and add that to the x scalar component of C. Add the x components to get the x component of the sum. Then separately, add the y scalar components of A, B, and C to get the y scalar component of the sum. So add up x components and separately add up y components. Never mix components. That is a fundamental violation of what we call vector algebra. Vectors don't add that way. In other words, don't ever add ax to by or ay to bx. You can only add like components. Okay. Now, let me emphasize one more thing, and then I'm going to show you an animation with vector addition. This approach of working with components to get a resultant vector works if you're subtracting vectors too, or maybe doing a complicated calculation where you're adding and subtracting. Let's say I got the same vectors, A, B, and C, but now I want to do the following operation. I want to take A vector plus B vector and then minus C vector. Let's call that result for that S. It's not going to be the same vector that I called R, so let's give it a different symbol, S. How would you find S? Again, I'm assuming you know the scalar components of A, B, and C. The answer is use the components. I'll write it down here. I think you'll be able to see it. To find the x component of S, you take the x component of A plus the x component of B minus the x component of C. And then to find the y component of S, you take the y component of A plus the y component of B minus the y component of C. Just do whatever the required vector calculation is, but do it separately for x and y components. I hope that point is clear, but we'll be practicing with it in class. Now, let me show you an animation. Okay? From Wiley Plus. Oh, I beg your pardon, that looks like that is way too small, doesn't it? Let's expand that a bit. I do think you want to be able to see it. Hopefully that's better. Okay? All right, now, you can see you're looking down from above on an xy coordinate system, and there are two vectors. There's a blue vector right here, and if I mouse over it, you have to look carefully, but there is a label, A arrow, so that vector is A. Down here is its scalar component, AX, and its scalar component over here, AY. There we go. Then we have head to tail with that one, a second vector, b arrow. Notice here's its x scalar component, bx, and its y scalar component, by. Note how this animation draws little right triangles for each of these vectors. There's a right triangle made out of blue arrows and a right triangle made out of red arrows. The blue one is for the A vector, and the red one is for the B vector. And I want to add those two. I want to take A plus B, and I'll call the resultant R. Let me now click this to show the sum. It'll be a black arrow. Just look at the full arrows. There's the blue one for A. There's B in head to tail configuration. So if we just did the graphical way of adding vectors to get R, that's the black arrow, we would draw R from the tail of the first to the head of the second. And that's exactly what the R would be, right there. Once we draw the R, we can also sketch its components, right? Make the right triangle for R. There's R sub x. How easy to mouse over these. There it is. And there's R sub y. Okay? All right, so blue arrow plus red arrow gives black arrow, you might say. A plus B equals R. But now I want to show you how to do the addition by using components. All right? To get the x component of R, you can look up on the screen there. You take AX plus BX. Here's the x component of R. Let's see if we get that by taking the components of A and B. Now, notice it says down here that the grid spacing is 2 kilometers. So we ought to be able to just read off the scalar components of A and B and R and so forth from the picture. All right, so take just a moment and think about it. You can even pause the video if you want to. What is A sub x? Okay, did you think about it? Did you try it for yourself? Here's A sub x down here. You can see it's 2 grid spacings long, and its arrow is in the positive direction. So A sub x is 4 kilometers. Just from looking at the diagram, at this animation, the simulation, we can see that. So A sub x is 4 kilometers. Now I want you to see if you can get B sub x. Again, pause the video if you want to think carefully, and then come back. Okay, so did you think about B sub x here? It's 3 grids long, that's be 6 kilometers, and the arrow points at negative x, so it's negative 6. Now add the x components. Add ax and bx. 4 kilometers minus 6 kilometers equals negative 2 kilometers. You have to do the algebra correctly. That's what r sub x must be. Now look at the r sub x. It's this black arrow, right? That's r sub x. If I can get it to show up. It's 1 grid spacing, that's 2 kilometers, and the arrow points in the negative x direction, so it's negative 2. Just like what I got by taking ax plus bx. Okay, now try the same thing for y components. First tell me, what's the y component of A? What's A sub y? Again, feel free to pause the video, think about it. Well, you can see it's 2 grid spacings, so that's 4 kilometers, and the arrow points in the plus y direction, so positive 4 kilometers. All right, now what's B sub y? Did you say negative 2 kilometers? Now, take A sub y plus B sub y. What do you get? 4 kilometers plus negative 2 kilometers is positive 2 kilometers. So that's AY plus BY. Now, look at the black arrow right here and tell me from that. Not easy to get it to appear. Let me try to mouse it. There it is. What RY is. Did you say positive 2 kilometers? That's what that black arrow tells you. But that's exactly what we got from AY plus BY. So the simulation is trying to show you how, when you add the x components of the vectors A and B, you get the x component of R. When you add the y components of the vector A and B, you get the y components of R. Just add x components and then add y components. And this simulation lets you move these arrows around. You can put them anywhere you want, okay? Anywhere you want. And convince yourself that when you add ax to bx, you'll get rx, and when you add ay to by, you'll get ry. If you ever want to play with these simulations, you can do so easily on your own. Just go to Wiley Plus and go to Read, Study, Practice, and then there are simulations. There's a link for opening the simulations. Okay? Okay, so we will be practicing in class with the concept of unit vectors and vector addition and subtraction by components. Very important process that we'll be using a lot. But that's all now for this